You know that feeling when someone uses a word, a technical term, some concept that you're pretty sure you were supposed to learn at some point, and you just nod? You nod and move on, and somewhere in the back of your mind, there's this tiny flicker of guilt because you think, I should know this. I should know what entropy actually means. I should understand why alternating current won out over direct current. I should be able to explain why a plane stays in the air without just waving my hands and saying, lift. And the thing is, you're not alone in that. Almost everyone carries around a small collection of ideas they were never properly taught. Not because they're not smart enough, but because the explanation came at the wrong time, or it came too fast, or it came wrapped in so much jargon that the meaning just slid right off. So tonight, let's fix that. Not all of it, obviously. But let's pick up some of those ideas, the ones that really matter, the ones that sit underneath so much of how the modern world actually works, and let's walk through them slowly. No rush, no test at the end. Just you and me and a quiet conversation about how things work and why they work that way, and who figured it all out. And if you fall asleep somewhere in the middle, that's perfectly fine. That's kind of the point. The ideas will still be here. Let's start with something that seems almost embarrassingly basic, but is actually one of the most misunderstood ideas in all of science and engineering. Energy. You've heard the word 10,000 times. You pay for energy every month when the electric bill shows up. You talk about having energy or not having energy. But what is it really? And here's the thing. Even physicists will tell you that energy is a surprisingly slippery concept to pin down. Richard Feynman, who was one of the greatest physicists of the 20th century, once said something like, "It is important to realize that in physics today, we have no knowledge of what energy is." And he wasn't being coy. He was being honest. What we know is that energy is a quantity that is conserved. It doesn't get created. It doesn't get destroyed. It just moves around and changes form. And that's actually the key insight, the one that took humanity centuries to arrive at. Go back to the early days. Ancient Greeks had ideas about motion and force, but they didn't have a concept of energy as we understand it. They thought about things in terms of what they could see. Objects moving, fires burning, water flowing downhill. It wasn't until the 17th century that people started getting precise about it. Gottfried Wilhelm Leibniz, the German philosopher and mathematician, the same person who independently invented calculus around the same time as Newton, which led to one of the most bitter intellectual feuds in history. But that's another story. Leibniz proposed something he called vis viva, which is Latin for living force. He noticed that if you took the mass of a moving object and multiplied it by the square of its velocity, you got a quantity that seemed to be conserved in certain types of collisions. Not the speed itself, not the momentum exactly, but this other thing, mass times velocity squared. And he was basically right. What he'd found was closely related to what we now call kinetic energy, the energy of motion. The modern formula is 1/2 times mass times velocity squared, so he was off by a factor of 2. But the core insight was there. There's something about a moving object, some quantity you can calculate, that doesn't just vanish. It goes somewhere. Now, think about what that means in your everyday life. When you're driving your car at 60 miles per hour and you hit the brakes, the car slows down. The kinetic energy decreases, but it doesn't disappear. It turns into heat. The brake pads get hot. That's the kinetic energy being converted into thermal energy through friction. And here's a detail that catches people off guard. Because kinetic energy depends on velocity squared, doubling your speed doesn't just double your energy, it quadruples it. Going from 30 to 60 miles per hour doesn't mean you need twice the braking distance. you need 4 times the braking distance. That's why highway accidents are so much more severe than fender benders in parking lots. It's not a linear relationship, it's a squared one. And that little mathematical fact, velocity squared, has enormous real-world consequences that most people never think about. But kinetic energy is just one flavor. There's potential energy, which is stored energy. Energy that's waiting to be converted into something else. A book sitting on a shelf has gravitational potential energy. It's not doing anything right now, but if it falls, gravity will accelerate it, and by the time it hits the floor, all that potential energy will have been converted into kinetic energy, and then into sound and a little bit of heat when it lands. A compressed spring has elastic potential energy. A battery has chemical potential energy. Food has chemical potential energy too, which is why we talk about calories. A calorie is literally a unit of energy. When you eat an apple, your body is extracting stored chemical energy and converting it into the mechanical energy of your muscles, the electrical energy of your nerve signals, and the thermal energy that keeps your body at 98.6 degrees. You are, in a very real sense, a biological engine that runs on chemical fuel. And that word, engine, brings us to one of the most important and most confusing ideas in all of physics. Thermodynamics. Don't let the word scare you. Thermo means heat. Dynamics means motion or change. It's the study of how heat moves and what happens when it does. And the reason it matters so much is that thermodynamics governs the fundamental limits of what any machine, any process, any system can actually do. It tells you what's possible and what's not. And it grew directly out of a very practical problem: how to build a better steam engine. This is the late 1700s, early 1800s. The Industrial Revolution is getting underway, first in Britain, and steam engines are the technology that's making it all happen. They're pumping water out of coal mines. They're powering factories. They're starting to drive locomotives. But they're also incredibly inefficient. Early steam engines, like the ones Thomas Newcomen built starting around 1712, converted maybe 1 or 2% of the heat energy from burning coal into useful mechanical work. 98% of the energy was just wasted, and people knew this was a problem, but they didn't have the theoretical framework to understand why or how much better things could get. Enter a young French military engineer named Sadi Carnot, and his story is one of those quiet tragedies that science is full of. Carnot was born in 1796, the son of a prominent French politician and military leader. He trained as an engineer, and in 1824, at the age of 28, he published a slim book with a long title that's usually shortened to Reflections on the Motive Power of Fire. And in that book, working almost entirely from first principles and thought experiments, Carnot figured out something profound. He showed that no heat engine, not just the clunky steam engines of his day, but any heat engine that could ever be built, could convert all of its heat into work. There was a fundamental, unavoidable limit, and that limit depended on the temperature difference between the hot source and the cold sink. Think about it this way. A steam engine works by heating water to create steam, which expands and pushes a piston, and then the steam has to be cooled and condensed so the cycle can repeat. You need a hot side and a cold side. Carnot realized that the maximum possible efficiency depends on how big the temperature gap is between those two sides. The bigger the gap, the more work you can extract. But you can never get 100%. There will always be some heat that flows to the cold side without doing useful work. Always. It's not a limitation of our engineering skill. It's a law of nature. And here's the sad part of Carnot's story. He published this brilliant work, and almost nobody noticed. The book sold poorly. The scientific establishment largely ignored it. And then, in 1832, at the age of 36, Carnot died of cholera during an epidemic in Paris. Most of his papers were burned, as was the custom with the belongings of cholera victims, to prevent the spread of disease. It wasn't until years later that other scientists, particularly Émile Clapeyron and later Rudolf Clausius and William Thomson, who became Lord Kelvin, rediscovered Carnot's work and recognized its importance. They built on his ideas to formulate the first and second laws of thermodynamics, which are arguably the most universal laws in all of physics. The first law is essentially conservation of energy. Energy can't be created or destroyed, only converted from one form to another. This is what Leibniz was groping toward with his vis viva, but now stated as a universal principle. The second law is the tricky one, the one that trips people up, and it's where entropy comes in. And entropy is one of those words that gets thrown around a lot, often incorrectly, so let's take a moment with it. The second law of thermodynamics says, in one of its many equivalent formulations, that heat flows spontaneously from hot things to cold things, never the other way around. That might sound obvious. Of course, a hot cup of coffee cools down in a cold room. You've never seen a cup of coffee spontaneously get hotter while the room gets colder. But think about why that's interesting. The first law, conservation of energy, wouldn't be violated if the coffee got hotter and the room got colder. The total energy would still be the same. There's nothing in the first law that prevents it. But it never happens. The second law is the reason. And entropy is the quantity that captures this directionality, this one-wayness of natural processes. Entropy, at its most basic, is a measure of how spread out or dispersed energy is. When the hot coffee transfers heat to the cool room, energy is spreading out, becoming more evenly distributed. Entropy increases. And the second law says that in any spontaneous process, the total entropy of the universe either stays the same or increases. It never decreases on its own. This is why you can't unscramble an egg. It's why perfume diffuses through a room but never spontaneously gathers back into the bottle. It's why time seems to have a direction. In fact, some physicists argue that entropy is the arrow of time. It's the thing that distinguishes the past from the future at a fundamental level. Now, this doesn't mean you can't decrease entropy locally. You can. Your refrigerator does it every day. It takes heat from the cold interior and pumps it to the warmer room. But it takes work to do that. The compressor uses electrical energy. And when you account for all the energy flows, including the waste heat from the compressor, the total entropy of the whole system, fridge plus room plus power plant, still increases. You can create pockets of order, but only by creating more disorder somewhere else. That's the deal. That's always the deal. Rudolf Clausius, the German physicist who formalized much of this in the 1850s and 1860s, put it beautifully. He summarized the two laws of thermodynamics in two short sentences. The energy of the universe is constant. The entropy of the universe tends to a maximum. And there's something almost poetic about that, isn't there? Everything that happens, every process, every reaction, every breath you take, is the universe's energy reshuffling itself, while entropy quietly, inexorably climbs. But let's bring this back down to earth, because thermodynamics isn't just abstract philosophy. It's the reason your car engine has a radiator. The engine burns gasoline, which is the hot source, and the radiator dumps waste heat to the air, which is the cold sink. Without that cold sink, the engine couldn't function. Carnot's insight from 1824 is literally built into every car on every road. It's why power plants are built near rivers or oceans. They need somewhere to dump their waste heat. It's why your laptop has a fan. Every computation your processor performs generates waste heat that has to go somewhere. And that's thermodynamics at work, right there in your lap. And this connects to something else that people often find confusing, something that sits right at the intersection of energy and thermodynamics and everyday life. The difference between energy and power. These two words get used interchangeably all the time, but they're not the same thing, and the distinction matters more than you might think. Energy is a quantity, an amount. Power is a rate. It's how fast you're using or producing energy. A battery stores energy, measured in watt-hours or kilowatt-hours. A light bulb uses power, measured in watts. A 60-watt bulb uses 60 joules of energy every second. Leave it on for an hour, and it's consumed 60 watt-hours of energy. Leave it on for 10 hours, 600 watt-hours. Same power, different total energy, because time matters. And this distinction becomes really important when you start talking about things like renewable energy and the electrical grid, because one of the biggest challenges isn't just generating enough energy. It's generating enough power at the right moment. The sun provides an enormous amount of energy over the course of a day, but it provides zero power at night. And the grid has to match supply to demand instant by instant, second by second. If demand exceeds supply even briefly, the frequency of the alternating current starts to drop, and if it drops too far, you get blackouts. Which brings us to something that most people encounter every single day without understanding it at all: alternating current, and why it won the war against direct current, and what that war was really about. And to understand that, we need to talk about a man named Nikola Tesla and another man named Thomas Edison, and a battle that shaped the entire electrical infrastructure of the modern world. So, let's get into it. Thomas Edison, by the late 1870s, was already famous. He was the Wizard of Menlo Park, the man who'd given the world the phonograph, who'd improved the telegraph, and who was now racing to do something even more ambitious: build a complete system for electric lighting. Not just invent a light bulb, though that was part of it. He wanted to build the whole thing: the generators, the wiring, the meters, the switches, the sockets, all of it. A complete ecosystem that would let you flip a switch in your home and have light appear. And Edison's system ran on direct current. DC, which is exactly what it sounds like: electricity flowing in one direction, steadily, like water through a pipe. Batteries produce direct current. It's simple, it's intuitive, and Edison understood it deeply. In September of 1882, he switched on the Pearl Street station in Lower Manhattan, and about 85 customers in a roughly 1 square mile area suddenly had electric light in their homes and offices. It was a genuine marvel. The New York Times building was one of those early customers, and the paper ran a glowing review, if you'll pardon the pun. Edison had done something extraordinary. He'd built a working power grid. But here's the thing. His system had a problem. And it was a physics problem, and it's one that connects directly back to what we were just talking about with power and energy. When you transmit electricity through a wire, some of that energy gets lost as heat. The wire has resistance, and the current flowing through that resistance generates waste heat. Now, the amount of power lost to heat follows a specific relationship. It's proportional to the square of the current times the resistance. This is sometimes called the I squared R loss, where I is the current. And that squared part is crucial. Double the current, and you don't double the losses, you quadruple them. Triple the current, and losses go up by a factor of 9. So if you're trying to send a lot of power over a long distance, you desperately want to keep the current low. But here's the catch. Power equals voltage times current. So if you want to deliver the same amount of power with less current, you need to increase the voltage. And this is where direct current hits a wall, because in Edison's era, there was no practical way to change the voltage of DC electricity. Whatever voltage you generated it at, that's the voltage it stayed at. And Edison's system ran at about 110 volts, which was safe for home use but terrible for transmission. At that voltage, you needed thick, expensive copper cables, and you could only send power about a mile before the losses became unacceptable. Which is why the Pearl Street station only served that tiny little patch of Manhattan. If you wanted to electrify a whole city, you'd need a power station on practically every block. It worked, but it didn't scale. Enter Nikola Tesla. And Tesla is one of those figures where the real story is so extraordinary that the myths that have grown up around him almost do him a disservice, because you don't need to exaggerate. The truth is remarkable enough. Tesla was born in 1856 in Smiljan, which was then part of the Austrian Empire, in what's now Croatia. His father was a Serbian Orthodox priest. His mother was, by Tesla's own account, extraordinarily inventive. She built household tools and mechanical devices despite having no formal education, and Tesla credited her with giving him his inventive instinct. As a young man, he studied engineering in Graz, Austria, and it was there, during a lecture, that he first encountered a Gamma dynamo, an early electrical generator that could also run as a motor. The device used direct current, and it had these components called commutators and brushes that were needed to keep the current flowing in the right direction. They sparked. They wore out. They were, in Tesla's view, inelegant. And right there in that lecture hall, he told his professor that there had to be a better way. A way to build a motor without those troublesome brushes. His professor reportedly told him it was impossible. That the idea contradicted the fundamental principles of how electric motors worked. Tesla spent years thinking about this problem, and the solution came to him, famously, during a walk in a park in Budapest in 1882, the same year Edison was firing up Pearl Street Station. Tesla was walking with a friend, reportedly reciting poetry, Goethe's Faust, of all things, when the complete vision of a new kind of motor appeared in his mind. He later said he could see it as clearly as if it were physically in front of him. He grabbed a stick and drew diagrams in the dirt. What he'd conceived was the alternating current induction motor, and it was brilliant. Instead of using direct current that flows one way, it used alternating current that reverses direction many times per second. In the United States, that frequency would eventually be standardized at 60 cycles per second, 60 hertz. In most of Europe, 50 hertz. And here's what's clever about Tesla's motor. You arrange multiple coils of wire around the outside of the motor, and you feed them alternating current, but you offset the timing. Each coil gets its current slightly out of phase with the next one. This creates a rotating magnetic field, a magnetic field that smoothly sweeps around the inside of the motor like a searchlight beam spinning in a circle. And if you put a simple metal rotor in the middle of that rotating field, the changing magnetic field induces currents in the rotor. That's Faraday's electromagnetic induction at work. And those induced currents create their own magnetic field, which interacts with the rotating field, and the rotor starts to spin. No brushes, no commutators, no sparking, no wearing parts. just a magnetic field dragging a piece of metal around in a circle. It's almost absurdly elegant. But the motor was only half the story. The real revolution was what alternating current made possible for power transmission. Because with AC, you can use a beautifully simple device called a transformer to change voltage levels. A transformer is just two coils of wire wrapped around a shared iron core. You feed alternating current into one coil, and the changing magnetic field it creates induces a current in the other coil. And here's the magic. The ratio of the voltages equals the ratio of the number of turns in each coil. If the second coil has 10 times as many turns as the first, you get 10 times the voltage out. And because power is conserved, roughly minus small losses, when the voltage goes up, the current goes down proportionally. So now you can do exactly what Edison couldn't. You generate electricity at a moderate voltage, step it up to thousands or even hundreds of thousands of volts for long-distance transmission, which means tiny currents and minimal I²R losses. And then step it back down to safe voltages at the other end for use in homes and businesses. The same amount of power carried over vast distances with thin, inexpensive wires. That changes everything. That's the difference between a power station on every block and a power station 50 miles outside the city. Tesla arrived in New York in 1884 with almost nothing, a few cents in his pocket, a letter of introduction, and a head full of ideas. He actually worked for Edison briefly. The details of their working relationship are somewhat disputed, but what's clear is that it didn't last long and didn't end well. Tesla claimed Edison promised him a substantial bonus for improving Edison's DC generators, and when Tesla delivered, Edison laughed it off as a joke. Whether that's exactly how it happened, we can't be sure, but Tesla left and eventually found backing from George Westinghouse, a powerful industrialist who immediately understood the potential of AC power. Westinghouse bought Tesla's patents and began building AC power systems, and this is where the so-called War of the Currents really heats up. Edison, who had invested enormously in DC infrastructure, fought back, and he fought dirty. He launched a public campaign to convince people that alternating current was deadly dangerous. He sponsored public demonstrations where animals were electrocuted with AC to show how lethal it was. He backed the development of the electric chair, which used AC, specifically so that alternating current would be associated with death in the public mind. It was by any measure a fear campaign, and it was cynical because direct current at equivalent voltages is just as dangerous as alternating current. The danger comes from the voltage and the current passing through your body, not from which direction it's flowing. But the engineering argument was overwhelming. A C was simply better for power distribution, and the numbers made that undeniable. The turning point came in 1893, when Westinghouse won the contract to light the world's Columbian Exposition in Chicago, an enormous World's Fair that drew 27 million visitors. The fair blazed with electric light, powered by Tesla's AC system, and it was spectacular. Then, even more decisively, Westinghouse and Tesla won the contract to build a hydroelectric power plant at Niagara Falls, which began operating in 1895. Power from Niagara was transmitted to Buffalo, New York, 26 miles away, with remarkable efficiency. That simply could not have been done with Edison's DC system. The war was effectively over. Now, what's fascinating is that this whole battle, this enormous industrial and personal conflict, ultimately came down to a transformer. That humble device with two coils and an iron core. The ability to step voltage up and down is what made long-distance power transmission practical, and that ability only works with alternating current because transformers rely on changing magnetic fields, and direct current doesn't change. It just sits there, steady. So the entire shape of our electrical infrastructure, the fact that power plants can be far from cities, that enormous generating stations can serve millions of people, that you can flip a light switch in your bedroom and draw power from a plant burning coal or spinning turbines 100 miles away. All of that traces back to a fundamental property of electromagnetism and a remarkably simple device. And Tesla, for all his genius, died in relative obscurity in 1943, alone in a New York hotel room, largely forgotten by the public that was living inside the electrical world he'd helped create. Westinghouse had paid him generously for his patents, but Tesla spent lavishly on further experiments, many of which didn't pan out, and he ended his life in financial difficulty. Edison, meanwhile, is the name most people remember. There's a lesson in there somewhere about how history treats inventors versus businessmen, but that's maybe a thought for another time. What I want you to notice, though, is how all of these ideas connect. We started with energy, with the ancient question of what makes things move and change. We followed that through thermodynamics, through entropy, through the distinction between energy and power. And now we've arrived at the electrical grid, this vast humming infrastructure that embodies all of those principles simultaneously. The generators convert mechanical energy to electrical energy. The transmission lines lose some of that energy to heat, exactly as the second law of thermodynamics would predict. The transformers manage the trade-off between voltage and current to minimize those losses, and the whole system has to balance power, supply and demand, instant by instant, or the frequency drifts and things start to go wrong. And frequency is actually a really interesting thing to think about, because it connects to another concept that people often find mysterious and slightly intimidating, something that shows up everywhere from music to radio to quantum mechanics, and that's the idea of waves and frequency and what it really means for something to oscillate. Because alternating current is, at its heart, a wave. The voltage rises and falls and reverses 60 times a second in the US, 50 in Europe, tracing out a smooth, repeating curve that mathematicians call a sine wave. And that sine wave shape isn't arbitrary. It emerges naturally from the way generators work. From a coil of wire spinning inside a magnetic field, the voltage at any instant proportional to the sine of the angle of rotation. But to really understand why that matters, and why waves show up in so many different places in physics, we need to talk about something that might seem unrelated at first: a vibrating string, and a French mathematician named Joseph Fourier, and an idea so powerful that it fundamentally changed how we understand the physical world. Fourier was born in 1768 in Auxerre, a small town in central France, and his early life was anything but easy. He was orphaned by the age of 9, both parents gone before he turned 10. But he was brilliant, and he was lucky enough to attract the attention of people who recognized that brilliance. He ended up getting a decent education through a local military school run by Benedictine monks, and he showed an early gift for mathematics that was, by all accounts, extraordinary. He got swept up in the French Revolution, nearly lost his head. Literally, he was arrested during the Terror and came very close to the guillotine, and then somehow ended up accompanying Napoleon on the Egyptian campaign in 1798, where he helped catalog the scientific and cultural treasures of ancient Egypt. It's a wild biography. But the thing Fourier is remembered for, the thing that matters for our story tonight, happened after he came back from Egypt and settled into a quieter life as a regional administrator in Grenoble. He became obsessed with heat. Specifically, he wanted to understand how heat flows through solid objects. If you take a metal bar and heat one end with a flame, how does the temperature change along the length of the bar over time? This seems like a straightforward question, but when Fourier sat down to work out the mathematics, he ran into a problem that nobody had been able to solve cleanly. The equations describing heat flow, what we now call the heat equation, one of the most important partial differential equations in all of physics. Those equations were well behaved when you started with simple, smooth initial conditions. But real-world temperature distributions aren't always smooth. What if the initial temperature profile is jagged, or has sharp corners, or is some complicated shape that doesn't match any neat mathematical function? And here's where Fourier had his great insight, the one that made him immortal in the history of science. He claimed, and this was controversial, deeply controversial at the time, that any function, no matter how complicated or jagged or irregular, could be broken down into a sum of simple sine and cosine waves. Different frequencies, different amplitudes, all added together. You take enough of these smooth, regular waves and stack them on top of each other, and you can build up any shape you want: a square wave, a sawtooth, a spike, anything. Think about what that means for a second. A sine wave is the simplest, smoothest oscillation you can imagine. It's that gentle, rolling curve, like a perfect ocean swell. And Fourier is saying that if you take enough of these perfect swells, each one at a different frequency, each one at a different height, and you add them all together, you can create something that looks nothing like a smooth wave. You can create sharp corners, flat tops, sudden jumps. It's like saying you can build a skyscraper out of nothing but soap bubbles if you use enough of them and arrange them just right. Now, the mathematicians of Fourier's day, people like Lagrange, who was one of the most respected mathematicians alive, they didn't buy it. Lagrange thought Fourier was wrong. He couldn't accept that you could represent a function with sharp discontinuities as a sum of perfectly smooth sine waves. And to be fair, the rigorous mathematical proof that Fourier was right in general took decades to work out. It wasn't fully settled until Dirichlet and others came along and established the precise conditions under which Fourier's claim holds. But Fourier was essentially right. And the technique he developed, breaking complex signals into their component frequencies, became one of the most powerful tools in all of science and engineering. We call it Fourier analysis, or Fourier decomposition, and it is everywhere. Let me give you a concrete example of why this matters. Think about sound. When you hear a musical note, say, middle C played on a piano, the air pressure at your eardrum is oscillating. It's vibrating back and forth, pushing and pulling on that tiny membrane, and your brain interprets that vibration as sound. The fundamental frequency of middle C is about 261.6 Hertz, meaning the air pressure oscillates about 262 times per second. But here's the thing. If you played middle C on a piano and middle C on a violin, they're the same note, the same fundamental frequency, but they sound completely different. You'd never confuse them. Why? Because neither instrument produces a pure sine wave. The piano string vibrates at 262 Hertz, yes, but it also vibrates at 524 Hertz, twice the fundamental, and at 786 Hertz, 3 times the fundamental, and at 4 times, and 5 times, and so on. These are called harmonics, or overtones, and the violin does the same thing, but with different relative strengths for each harmonic. The particular recipe of harmonics, how much of the second, how much of the third, how much of the fifth, that's what gives each instrument its distinctive character, its timbre. And what Fourier analysis lets you do is take the complex, messy waveform that comes out of a piano or a violin or a human voice and decompose it into its individual frequency components. You can see exactly how much energy is at each frequency. It's like having a prism for sound. Just as a glass prism takes white light and spreads it out into its component colors, each color being a different frequency of electromagnetic wave. Fourier analysis takes a complex signal and spreads it out into its component frequencies. And this isn't just an abstract mathematical trick. It's the foundation of how your phone works, how digital music works, how noise-canceling headphones work, how MRI machines produce images of the inside of your body. Every time you make a phone call, your voice is captured by a microphone, converted into an electrical signal, and then Fourier analyzed into its frequency components so it can be efficiently compressed and transmitted. When you listen to an MP3 file, the compression algorithm used Fourier analysis to figure out which frequency components of the original recording your ear would barely notice if they were removed, and it threw those away to make the file smaller. When noise-canceling headphones listen to the ambient sound around you and generate an anti-noise signal to cancel it out, they're working in the frequency domain. They're doing Fourier analysis in real time, hundreds of times per second. So Fourier gave us this incredibly powerful lens for understanding the world, and it connects back to what we were talking about with alternating current. The AC power grid operates at a specific frequency, 60 Hz in North America, 50 Hz in most of Europe, and that frequency has to be maintained with remarkable precision. If the frequency drifts even a fraction of a hertz, it can cause problems for sensitive equipment, and the reason we can analyze and control and filter electrical signals so effectively is because of Fourier's insight that any signal, no matter how complex, is really just a stack of sine waves. But here's where I want to introduce another concept that people often find confusing, one that's deeply related to waves and frequency, and that's the idea of resonance. You've probably heard the word before, maybe in the context of an opera singer shattering a wine glass with their voice, or a bridge swaying dangerously in the wind. Resonance is one of those concepts that sounds dramatic, and it can be, but at its core it's beautifully simple. Every physical object that can vibrate has what's called a natural frequency, a frequency at which it prefers to vibrate. Push a child on a swing, and you'll notice that the swing has a natural rhythm to it. If you push at exactly the right moment, at the natural frequency of the swing, each push adds to the motion, and the swing goes higher and higher. Push at the wrong time, and you're fighting against the motion, and nothing much happens. That's resonance. It's what happens when you apply a periodic force to a system at or near its natural frequency. The energy from each cycle of the force accumulates in the system, and the amplitude of the vibration grows and grows. The wine glass thing is real, by the way. A crystal. Wine glass has a natural frequency. You can hear it if you wet your finger and run it around the rim, producing that clear singing tone. If a singer produces a note at exactly that frequency and sustains it with enough volume, the sound waves push on the glass in sync with its natural vibration. Each cycle of the sound wave adds a tiny bit more energy to the glass's oscillation. The amplitude of the vibration grows until the glass physically can't flex enough to accommodate it, and it shatters. It takes a very skilled singer and a very specific glass, but it genuinely works. Now, resonance in engineered structures is a much more serious matter, and the most famous example, the one that every engineering student learns about, is the Tacoma Narrows Bridge. This was a suspension bridge in Washington State that opened on July 1st, 1940. From almost the very beginning, the bridge had a tendency to move in the wind. It would undulate vertically. The road deck would rise and fall in gentle waves, and locals actually nicknamed it Galloping Gertie because of this bouncing motion. People would drive across it and see the cars ahead of them disappear and reappear as the road surface rolled beneath them. Some people actually drove across it on purpose for the thrill, like a roller coaster. On November 7th, 1940, just 4 months after it opened, a steady 42-mile-per-hour wind set the bridge into increasingly violent oscillations. But here's what's important to understand. It wasn't just bouncing up and down anymore. The motion shifted into a twisting mode, a torsional oscillation, where one side of the road deck would rise while the other side fell, and then they'd switch. The bridge was literally wringing itself like a towel. The amplitude of this twisting grew and grew over the course of about an hour, and eventually the bridge tore itself apart. Huge sections of the road deck broke free and fell into the Puget Sound below. Remarkably, only one life was lost, a dog named Tubby, stranded in a car on the bridge, who bit a rescue worker who tried to save him and couldn't be retrieved in time. The footage of the collapse, shot by a local camera shop owner named Barney Elliott, is some of the most dramatic engineering failure footage ever recorded, and it's still shown in physics and engineering classes around the world. Now, for decades, the Tacoma Narrows collapse was explained in textbooks as a straightforward case of resonance. The wind happened to gust at the bridge's natural frequency, and the bridge resonated itself to destruction. But the real story is more nuanced and more interesting than that. The wind that day was steady, not gusting rhythmically. What actually happened involves a phenomenon called aeroelastic flutter, which is a self-exciting feedback loop between the wind, the structure's motion, and the aerodynamic forces acting on the structure. As the bridge deck twisted slightly, the change in angle altered the way the wind flowed over and under it, creating aerodynamic forces that pushed the twist further. And as the twist reversed, the aerodynamic forces reversed too, always in a way that fed energy into the oscillation. It's related to resonance. The system was being driven at its natural torsional frequency. But the driving force wasn't an external periodic push, like someone timing their pushes on a swing. The driving force was generated by the motion itself. The bridge was, in a sense, flapping itself to death. And this distinction matters because it affects how you design against it. If the problem were simple resonance from periodic wind gusts, you could solve it by changing the bridge's natural frequency so it didn't match typical wind patterns. But aeroelastic flutter is sneakier. It can occur at any wind speed above a certain threshold, regardless of whether the wind is gusty or steady. The solution is to change the aerodynamic profile of the structure so that the feedback loop can't establish itself, or to add enough damping, enough energy-absorbing capacity, that the oscillations can't grow even if the feedback loop tries to start. The replacement bridge, which opened in 1950, was much heavier and stiffer, with deep stiffening trusses along the sides that gave the road deck a much more aerodynamically stable profile. And every major suspension bridge designed since then has been tested in wind tunnels, scale models subjected to simulated wind conditions to make sure the same kind of flutter can't develop. The Tacoma Narrows failure changed bridge engineering permanently. But resonance and oscillation show up in places far beyond bridges, and one of the most profound is in the way we understand light itself. Because light, it turns out, is a wave. Or at least, it behaves like one under many circumstances. And the story of how we figured that out, and what it means for light to have a frequency, and how that connects to color and heat, and eventually to the most revolutionary idea in all of 20th century physics, that story starts with a bitter rivalry between two giants of British science and a crucial experiment involving two slits cut into a piece of card. The experiment is deceptively simple, and the person who devised it was a man named Thomas Young, and his story is one of those lives that makes you feel a little inadequate. Honestly, because the man was almost absurdly talented at everything he tried. Born in 1773 in Somerset, England, Thomas Young could read by the age of 2. By 14, he had taught himself Greek, Latin, French, Italian, Hebrew, Arabic, Persian, and a handful of other languages. He went on to study medicine, became a physician, and along the way made contributions to so many fields, optics, physiology, linguistics, Egyptology, that people started calling him the last man who knew everything. He was one of the key figures in deciphering the Rosetta Stone, for instance, which is a whole other story. But the thing that matters most for us tonight is what he did with light. Now, to understand why Young's experiment was so important, you need to know what he was arguing against, and the person on the other side of that argument, at least in spirit, was Isaac Newton. Newton had been dead for nearly a century by the time Young was doing his work, but Newton's ideas about light were still dominant, still treated almost as gospel. Newton believed that light was made of tiny particles. He called them corpuscles, little bullets of light shooting out from a source in straight lines. And this made intuitive sense. Light travels in straight lines. It casts sharp shadows. It bounces off mirrors the way a ball bounces off a wall. The particle theory explained all of that beautifully. But there had always been another camp. Back in the late 1600s, a Dutch scientist named Christian Huygens had proposed that light was a wave, more like sound or ripples on water. And Huygens' wave theory could explain some things that Newton's particles struggled with, like why light bends slightly when it passes from air into glass, or why you sometimes see faint colored fringes around shadows if you look very carefully. But Newton's reputation was so enormous, so towering, that for more than 100 years after his death, most scientists simply accepted the particle theory and moved on. Thomas Young didn't. And here's what he did. He took a beam of sunlight, passed it through a tiny pinhole to create a narrow, coherent source, and then let that light fall on a screen with 2 very thin, closely spaced slits cut into it. Behind the slits, he placed another screen to catch whatever pattern the light made. Now, if light were made of particles, you'd expect to see 2 bright bands on the far screen, one behind each slit, like 2 streams of bullets passing through 2 doorways. Simple, clean, 2 stripes of light. That's not what happened. What Young saw instead was a pattern of alternating bright and dark bands, many bands, not just 2, spread across the screen, an interference pattern. And this is the key. If you've ever watched 2 sets of ripples on a pond collide, you've seen interference. Where 2 wave crests meet, they add together and make a bigger wave. That's constructive interference, and it produces a bright band. Where a crest meets a trough, they cancel each other out. That's destructive interference, and it produces darkness. The only way you get an interference pattern is if light is behaving as a wave. Particles don't cancel each other out. 2 bullets passing through 2 slits don't somehow annihilate each other and leave darkness. Only waves do that. Young published his results around 1801 to 1804, and the reaction was not great. The establishment pushed back hard. One particularly harsh review in the Edinburgh Review basically accused Young of being deluded, of wasting everyone's time, with a theory that contradicted Newton. The reviewer didn't even engage with the evidence. It was pure appeal to authority. Newton said particles, so it's particles. Young was genuinely hurt by the attacks, and for a while he pulled back from optics and focused on other things. But here's the thing about good evidence. It doesn't go away just because people don't like it. Within a couple of decades, a French engineer and physicist named Augustin Jean Fresnel independently developed a rigorous mathematical wave theory of light, complete with detailed predictions about diffraction and interference that matched experiments perfectly. Fresnel's work was so thorough, so precise, that even the skeptics had to start coming around. And by the 1820s and 1830s, the wave theory of light had essentially won. Newton's corpuscles were out. Light was a wave. And once you accept that light is a wave, a beautiful question opens up. What is it a wave of? Sound is a wave of pressure in air. Ocean waves are waves of displacement in water. What medium is light waving through? This was a genuine puzzle, and scientists proposed a substance called the luminiferous ether, a hypothetical material that filled all of space, invisible and weightless, but rigid enough to support the incredibly fast vibrations of light. The ether was supposed to be the medium through which light waves propagated, the way air is the medium for sound. And for decades, people just accepted this. The ether was out there, everywhere, and light was a ripple in it. We'll come back to the ether later, because the story of how it was disproven is fascinating and connects to Einstein and relativity. But for now, let's stay with what the wave theory of light actually tells us, because this is where it connects back to Fourier and frequencies and everything we were talking about earlier. If light is a wave, then it has a frequency, just like sound, just like the vibrations in a bridge, just like the AC current in your wall socket. And here's what's beautiful. The frequency of a light wave determines its color. Red light has a relatively low frequency, around 430 trillion cycles per second. Violet light has a higher frequency, about 750 trillion cycles per second. And everything in between, orange, yellow, green, blue, corresponds to frequencies in between. When you see a rainbow, you are literally seeing light sorted by frequency. It's a spectrum, a continuous sweep from low-frequency red to high-frequency violet, and every color you perceive is your brain's interpretation of a specific frequency of electromagnetic vibration hitting the cells in your retina. Think about that for a second. Color isn't really out there in the world. There's no redness floating around in space. What's out there is electromagnetic waves vibrating at different frequencies, and your eye has specialized cells, cone cells, that respond to different ranges of those frequencies, and your brain assembles those signals into the experience of color. It's a translation. The universe speaks in frequencies, and your brain translates that into the rich, vivid palette you see every day. And here's where Fourier sneaks back in, because white light, ordinary sunlight, the light from an incandescent bulb, isn't a single frequency. It's a mixture, a blend of many frequencies all jumbled together, just like a musical chord is a blend of many sound frequencies. When Newton famously passed white light through a glass prism and saw it spread into a rainbow, he was doing something conceptually very similar to a Fourier decomposition. The prism was separating the mixed signal of white light into its component frequencies. Each frequency bends by a slightly different amount as it passes through the glass, a phenomenon called dispersion, and so they fan out into a spectrum. Newton did this in 1666, more than a century before Fourier was born, and he didn't have the mathematical framework to describe it in terms of frequency decomposition. But that's exactly what it is. Now, there's something important lurking in this story about light and frequency, and it has to do with heat. You know that when you heat a piece of metal, say a poker in a fire, it starts to glow. First it glows a dull red, then orange, then yellow, and if you could get it hot enough, it would glow white and eventually bluish-white. The color of the glow tells you the temperature. This isn't just a rough correlation. It's a precise physical relationship. The hotter an object gets, the higher the peak frequency of the light it emits. Cooler objects emit mostly low-frequency radiation, infrared, which you can feel as warmth but can't see. Hotter objects emit higher frequencies, visible red, then yellow, then blue. The surface of our sun, at about 5,500 degrees Celsius, emits light that peaks in the yellow-green part of the spectrum, which is why sunlight looks the way it does. By the late 1800s, physicists were trying to write down a mathematical formula that would predict exactly how much light energy a hot object emits at each frequency. This seems like it should be straightforward, right? You measure the spectrum of a glowing object at a known temperature, you plot intensity versus frequency, and you find the equation that fits the curve. Physicists called this the black body radiation problem. A black body being an idealized object that absorbs all radiation and emits a smooth, predictable spectrum based solely on its temperature. And here's where things went very, very wrong. Or very, very right, depending on how you look at it. The classical physics of the time, the physics of Newton and Maxwell and Boltzmann, made a clear prediction about what that spectrum should look like. And the prediction worked beautifully at low frequencies. But at high frequencies, in the ultraviolet range and beyond, the classical formula predicted that the intensity of radiation should keep climbing higher and higher without limit. A hot object should emit infinite energy at ultraviolet frequencies. This was obviously catastrophically wrong. A warm cup of coffee does not blast you with lethal ultraviolet rays. The prediction was so absurd that physicists gave it a dramatic name: the ultraviolet catastrophe. The classical theory was broken. Something fundamental was missing from the picture. And the person who figured out what was missing, who patched the hole in a way that would ultimately demolish the foundations of classical physics and rebuild them into something stranger and more beautiful, was a quiet, meticulous German physicist named Max Planck. And what Planck did in the year 1900, almost as an act of desperation, was something he himself didn't fully believe in. He introduced a mathematical trick. That's really how he thought of it. Not as a deep truth about reality, but as a clever workaround to make the math behave. What Planck proposed was that energy, at the atomic level, couldn't be emitted or absorbed in any arbitrary amount. Instead, it had to come in tiny, discrete packets. He called these packets quanta, from the Latin word for how much, and the size of each packet was determined by the frequency of the radiation. Higher frequency meant bigger packets. Lower frequency meant smaller packets. The relationship was beautifully simple. The energy of one quantum equals the frequency multiplied by a constant, a tiny, almost absurdly small number that we now call Planck's constant. And here's why that fixed the ultraviolet catastrophe. Think about it this way. Under classical physics, energy was like water from a tap. You could pour any amount, no matter how small. So at every frequency, even extremely high ones, there was nothing stopping the atoms from radiating energy. The math said they should, and so the predicted intensity just kept climbing toward infinity as frequency increased. But with Planck's rule, the higher the frequency, the bigger each individual energy packet has to be. At very high frequencies, each quantum becomes so expensive, energy-wise, that atoms simply can't afford to emit them very often. It's like the difference between buying sand 1 grain at a time versus buying boulders. You can always afford another grain of sand, but eventually the boulders get too heavy to lift. The high-frequency radiation gets naturally suppressed, not by any arbitrary cutoff, but by the simple economics of energy packets getting too large. And when Planck plugged this assumption into the math, the resulting formula matched the experimental data perfectly, beautifully, at every frequency, at every temperature. The curve fit. But Planck was deeply uncomfortable with what he'd done. He was a conservative physicist by temperament, someone who revered the classical tradition. He spent years trying to find a way to derive his result without the quantum assumption, to show that energy was really continuous after all, and the quanta were just a mathematical convenience. He never succeeded. The quanta wouldn't go away. And then, in 1905, a young patent clerk in Bern, Switzerland, took Planck's idea and ran with it in a direction Planck himself would never have dared. Albert Einstein, 26 years old, working at the Swiss patent office because no university would hire him, published a paper arguing that light itself was quantized, not just the emission and absorption of light, but light itself. That light actually traveled as discrete particles, each carrying one quantum of energy. Einstein called them light quanta. We call them photons. Now think about what that means in the context of everything we've been talking about. Remember Young's double-slit experiment? The beautiful interference pattern that proved, seemingly beyond any doubt, that light was a wave? And here's Einstein saying no, actually, light is made of particles. It sounds like he's dragging physics back to Newton's corpuscular theory, back to the idea that Young and Fresnel had thoroughly demolished a century earlier. But Einstein wasn't saying light isn't a wave. He was saying something far stranger, that light is both, that it behaves like a wave when you're looking at how it propagates and interferes, but it behaves like a particle when you're looking at how it exchanges energy with matter. The specific problem Einstein used to make his case was the photoelectric effect, and it's worth slowing down on this because it's one of those experiments that seems simple, but cracks open the entire universe. The photoelectric effect had been observed since the 1880s. Heinrich Hertz noticed it, and Philip Lenard studied it carefully. Here's what happens. You shine light on a metal surface, and electrons get knocked out of the metal. That's it. Light hits metal, electrons fly off. You can detect them, measure their energy, count them. Straightforward, right? But the details were baffling. If light were a classical wave, then brighter light, a wave with bigger amplitude, should knock out electrons with more energy. You'd expect that cranking up the brightness is like sending bigger ocean waves crashing against a dock. More force, more energy transferred to each electron. But that's not what happened. When you made the light brighter, you got more electrons, but each individual electron came out with exactly the same energy as before. And when you changed the color of the light, the frequency, that's when the energy of each electron changed. Higher frequency light produced higher energy electrons. Below a certain frequency, no electrons came out at all, no matter how blindingly bright you made the light. A dim ultraviolet lamp could knock electrons loose, but the most powerful red spotlight in the world couldn't free a single one. Classical wave theory had absolutely no explanation for this. But Einstein's photon idea explained it instantly. If light comes in packets, and each packet's energy depends on its frequency, then each photon either has enough energy to knock an electron free, or it doesn't. Making the light brighter just means more photons, more chances to knock out electrons. But each individual collision is still one photon hitting one electron. If the photon's frequency is too low, it simply doesn't carry enough energy to overcome the electron's binding energy, and no amount of brightness, no flood of low-energy photons can change that. It's like trying to break down a door. 1,000 people gently leaning on it won't do what one person with a battering ram can. Einstein's explanation was elegant, quantitative, and it matched every observation perfectly. It was also the paper that eventually won him the Nobel Prize. Not relativity, not E equals mc squared, but the photoelectric effect. The Nobel Committee in 1921 specifically cited his work on the law of the photoelectric effect. There's something quietly wonderful about that. But here's the thing that should keep you up at night. Well, maybe not tonight. Tonight you're trying to sleep. But the thing that haunted physicists for decades: how can light be both a wave and a particle? Young's experiment shows interference, which is fundamentally a wave phenomenon. Einstein's photoelectric effect shows discrete energy packets, which is fundamentally a particle phenomenon. Both experiments are real. Both results are repeatable. Light isn't choosing one identity or the other based on which experiment you like better. It's genuinely, stubbornly, irreducibly both. And this is where quantum mechanics starts to feel less like physics and more like philosophy. Because in the 1920s, physicists discovered that it wasn't just light that had this dual nature. Matter did too. In 1924, a French graduate student named Louis de Broglie, and his name is pronounced roughly de Broglie, which trips up almost everyone the first time, proposed in his doctoral thesis that if light waves could behave like particles, then maybe particles could behave like waves. He suggested that every particle, every electron, every atom, every object has an associated wavelength. The faster and heavier the particle, the shorter the wavelength. For anything large enough to see or hold, the wavelength is so unimaginably tiny that wave behavior is completely undetectable. A baseball has a de Broglie wavelength, but it's trillions of times smaller than an atomic nucleus. You will never, ever see a baseball diffract through a doorway. But for something as light as an electron, the wavelength is roughly the size of an atom. And at that scale, wave behavior becomes not just detectable, but dominant. De Broglie's thesis committee wasn't sure what to make of it. The idea was so radical that they sent it to Einstein for review. Einstein read it and reportedly said it was a very interesting idea, which, from Einstein, was high praise. De Broglie got his doctorate, and 3 years later, in 1927, Clinton Davison and Lester Germer at Bell Labs accidentally confirmed the whole thing. They were firing electrons at a nickel crystal, and the electrons produced a diffraction pattern, the same kind of pattern you get when waves pass through a grating. Electrons, those tiny bullets of matter that we'd been thinking of as particles since J.J. Thomson discovered them in 1897, were behaving like waves. The experiment wasn't even designed to test de Broglie's hypothesis. Davison and Germer were studying something else entirely, and the wave behavior showed up uninvited, undeniable, and impossible to explain any other way. So now you've got this extraordinary situation. Light, which everyone thought was a wave, turns out to also be a particle. Electrons, which everyone thought were particles, turn out to also be waves. And the bridge between the two descriptions is Planck's constant, that tiny number that Planck introduced as a desperate mathematical trick in 1900. It shows up everywhere. It's in the energy of a photon. It's in the wavelength of an electron. It sets the scale at which quantum behavior becomes important. Below that scale, the universe plays by rules that feel alien to us. Above it, classical physics works just fine, which is why you never noticed any of this in your daily life. And this is actually a really important point to sit with for a moment. Quantum mechanics isn't a replacement for classical physics, it's a deeper layer. Classical physics, Newton's laws, Maxwell's equations, thermodynamics, all of that still works beautifully for the world you can see and touch. When you throw a ball, you don't need to calculate its de Broglie wavelength. When you design a bridge, you don't need to worry about the wave nature of steel beams. Classical physics is what happens when quantum effects average out over billions and billions of particles, and the averages are so reliable that the underlying quantum weirdness becomes invisible. It's like how you can predict traffic flow on a highway without knowing what each individual driver is thinking. The macro behavior emerges from the micro behavior, but it's so smooth and predictable that you'd never guess the chaos underneath. But sometimes the quantum level reaches up and touches the everyday world in ways you don't expect. Semiconductors, the chips in your phone, your laptop, every piece of modern electronics work because of quantum mechanics. The way electrons behave in silicon, the way they tunnel through barriers they classically shouldn't be able to cross, the way their energy levels are quantized into bands with gaps between them. All of that is pure quantum physics, and without it, you don't get transistors, you don't get integrated circuits, you don't get the digital age. Every time you tap your phone screen, you're relying on principles that Einstein and Planck and de Broglie laid down over a century ago. And here's where things get even stranger. Because in the mid-1920s, a new generation of physicists, younger, bolder, less attached to classical intuition, started building the full mathematical framework of quantum mechanics. And the two people who did it, working independently, using completely different mathematical approaches, arriving at the same physical predictions through what looked like entirely unrelated theories, were Werner Heisenberg and Erwin Schrödinger. And the story of how these two very different men, with very different temperaments and very different philosophies, built what turned out to be two faces of the same theory. That story is one of the most fascinating rivalries in all of science. Heisenberg was in his early 20s, working on the island of Helgoland in the North Sea, suffering from hay fever so bad he'd retreated there to escape the pollen, when he had what might be the most productive bout of insomnia in scientific history. Picture this. It's June 1925. He's 23 years old. His eyes are swollen. His face is puffy. He can barely see. And he's been pacing around this rocky little island trying to work through a problem that had been nagging at him for months. His mentor, Niels Bohr, back in Copenhagen, had been pushing this idea that physics should only concern itself with things you can actually observe. Not what an electron is doing between measurements, not what orbit it's traveling in, not what path it takes. Just the quantities you can actually detect in the lab, the frequencies of light that atoms emit, the intensities of spectral lines, the measurable stuff. And Heisenberg took that philosophy and ran with it in a direction nobody expected. What he did, working through those sleepless nights on Helgoland, was strip away every mental picture of what an atom looks like. No little solar system with electrons orbiting a nucleus, no trajectories, no positions between measurements, and instead built a mathematical framework using only observable quantities. He arranged these quantities into tables of numbers, grids where each entry represented a transition between two energy states of an atom. He multiplied these tables together using specific rules and found, to his amazement, that the order of multiplication mattered. If you multiplied table A by table B, you got a different result than multiplying B by A. Now, that might sound like a minor mathematical curiosity, but think about what that means. In ordinary arithmetic, 3 times 5 equals 5 times 3. Always. That's a rule so basic you learned it before you could ride a bike. But Heisenberg's quantities didn't obey that rule. And when he realized this, he was genuinely disturbed by it. He later recalled being so unsettled that he climbed a rock on the island in the middle of the night and sat there watching the sun come up, wondering if he'd stumbled onto something real or if he'd made a terrible mistake. He hadn't made a mistake. What he'd independently rediscovered was matrix algebra, a branch of mathematics that had been developed decades earlier, but that most physicists at the time weren't particularly familiar with. When he brought his work back to Göttingen, his colleague Max Born recognized the mathematical structure immediately. Born, along with his student Pascual Jordan, helped Heisenberg formalize the whole thing into what became known as matrix mechanics. It was the first complete, self-consistent mathematical framework for quantum mechanics, and it worked. It predicted the right spectral lines, the right energy levels, the right transition probabilities, but almost nobody liked it. Here's the thing. Matrix mechanics was abstract, brutally abstract. There was nothing to visualize, no picture of what the electron was doing, no wave, no particle, no trajectory. Just arrays of numbers and multiplication rules. Physicists are human beings, and human beings like to have mental images of what's happening. Matrix mechanics gave you the right answers, but offered you nothing to hold on to, nothing to see in your mind's eye. It felt like a black box. You put in the initial conditions, you turned the mathematical crank, and out came predictions that matched experiments. But the question, what is actually happening inside the atom, was, according to Heisenberg's philosophy, not even a meaningful question to ask. And then, about 6 months later, along came Schrödinger, with something that felt completely different. Erwin Schrödinger was older, 38 in 1926, which made him practically elderly by the standards of quantum physics at the time. He was Austrian, charming, unconventional in his personal life in ways that raised eyebrows even in 1920s Europe, and he had a deep attachment to the classical tradition of physics. He loved continuity. He loved waves. He loved the elegant differential equations that had served physics so well since Newton. And when he encountered de Broglie's matter wave idea, the one we talked about earlier, where particles have wavelengths determined by Planck's constant divided by their momentum, Schrödinger saw an opportunity to build quantum mechanics on a foundation that felt familiar and beautiful. Over Christmas of 1925, Schrödinger retreated to a villa in the Swiss Alps, Arosa, a ski resort town, and in a burst of creative work that lasted just a few weeks, he derived his wave equation, the Schrödinger equation. You've probably heard the name even if you've never studied physics. It's one of those equations, like E equals mc squared or F equals ma, that has transcended its technical origins and become part of the cultural landscape. And what it describes is elegant in a way that matrix mechanics simply wasn't. It says that every quantum system has a wave function, usually written with the Greek letter psi, and this wave function evolves over time according to a specific differential equation. If you know the wave function at one moment, the equation tells you what it will be at every future moment. It's deterministic in that sense, which felt reassuring to physicists raised on Newton and Maxwell, and the predictions it made were identical to Heisenberg's. Every spectral line, every energy level, every transition probability. The same answers, derived from what appeared to be a completely different theory. Schrödinger himself proved that the two formulations were mathematically equivalent in 1926. Matrix mechanics and wave mechanics were the same theory wearing different clothes. It's a bit like discovering that two people who seem to speak entirely different languages are actually saying the same things, one in French and one in Mandarin. The grammar looks nothing alike. The vocabulary is unrecognizable, but the meaning is identical. But here's where the rivalry gets personal and honestly, kind of entertaining. Schrödinger and Heisenberg genuinely did not like each other's approaches. Heisenberg called Schrödinger's wave mechanics disgusting. That's a direct quote. He wrote to his friend Wolfgang Pauli, saying he found the whole wave picture repulsive. Schrödinger, for his part, said that he was discouraged, if not repelled, by matrix mechanics. Each man felt that the other was fundamentally wrong about what quantum mechanics meant, even though they agreed about what it predicted. And the deepest disagreement was about what the wave function actually represented. Schrödinger initially believed, or wanted to believe, that the wave function was a real, physical wave, that an electron literally was a wave, spread out in space, and that the wave function described its actual physical distribution. It was a comforting picture. You could visualize it. You could draw it. But it ran into problems almost immediately. When you actually detect an electron, you always find it at a specific point. It doesn't arrive as a spread-out smear. It hits the detector at one spot. So if the electron is really a wave, how does it suddenly collapse to a point when you look at it? The answer, or at least the answer that most physicists eventually adopted, came from Max Born, who proposed that the wave function doesn't describe the electron itself. It describes the probability of finding the electron. Specifically, the square of the wave function at any point gives you the probability density for finding the particle at that location. The wave function is a probability wave, not a physical wave. And this interpretation, which became known as the Born rule, earned Born the Nobel Prize in 1954, nearly 30 years after he proposed it. Think about what that means for a second. The most fundamental description of reality that physics can offer doesn't tell you what will happen. It tells you the likelihood of various things happening. The universe, at its deepest level, runs on probability, not because we're ignorant of some hidden mechanism, not because we just haven't figured out the details yet, but because, as far as anyone can tell, that's how nature actually works. When a radioactive atom decays, there is no hidden clock inside it ticking down. There's just a probability per unit time, and when it decays is genuinely, fundamentally random. This is what Einstein couldn't accept. His famous line, "God does not play dice," was aimed directly at this interpretation. Einstein never denied that quantum mechanics made correct predictions. He just couldn't believe that the randomness was fundamental. He spent the last 3 decades of his life searching for a deeper, deterministic theory underneath quantum mechanics. He never found one. And every experiment since has confirmed that the randomness is real, down to the most precise measurements we can make. Now, Heisenberg took the philosophical implications even further. In 1927, he published his uncertainty principle, and this is one of those ideas that's so widely misunderstood that it's worth taking a moment to get it right. The uncertainty principle doesn't say that our instruments are too clumsy to measure things precisely. It doesn't say that the act of measuring disturbs the system, though that's how it's often explained in textbooks, and even how Heisenberg himself first described it using a thought experiment about a microscope. What it actually says is deeper than that. It says that certain pairs of properties, position and momentum, energy and time, simply do not have simultaneously precise values. It's not that the electron has a definite position and a definite momentum, and we just can't know both. It's that having a perfectly defined position and a perfectly defined momentum at the same time is not a thing that exists in nature. And this connects back to something we explored earlier: Fourier analysis. Remember how any wave can be decomposed into sine waves of different frequencies? Well, a wave that has a very precise frequency has to be spread out over a long stretch of space. It's a pure, endless oscillation. And a wave that's tightly localized in space, a short pulse, has to be made up of many different frequencies mixed together. You can't have a wave that's both perfectly localized and perfectly single frequency. That's not a limitation of measurement. That's a mathematical property of waves themselves. And since quantum mechanics describes particles as waves, the same trade-off applies. The more precisely you pin down where a particle is, the more spread out its momentum becomes, and vice versa. Planck's constant, once again, sets the scale of this trade-off. It tells you exactly how much uncertainty you're stuck with. So by 1927, the full framework was in place. Schrödinger's equation tells you how the wave function evolves. Born's rule tells you how to extract probabilities from it. Heisenberg's uncertainty principle tells you what you fundamentally cannot know simultaneously. And the whole thing was synthesized into a coherent package at the famous Solvay Conference of 1927, where essentially every major physicist alive gathered in Brussels to argue about what it all meant. There's a photograph from that conference. You've probably seen it even if you don't know what it is. 29 physicists, 17 of whom were or would become Nobel laureates, posing on the steps of a building. Einstein is in the front row. Bohr is there. Heisenberg, Schrödinger, Born, Dirac, Pauli, de Broglie, Curie, Lorentz. It's the most extraordinary gathering of scientific talent ever captured in a single image. And the debates that happened at that conference shaped how we think about reality itself. The interpretation that emerged, largely championed by Bohr and Heisenberg, later called the Copenhagen interpretation, said essentially this: don't ask what's happening between measurements. The wave function is a tool for calculating probabilities of measurement outcomes. When you measure, you get a definite result. Between measurements, the question of what the system is really doing is not one that physics can or should answer. Not everyone was satisfied. Einstein certainly wasn't. De Broglie proposed an alternative, a pilot wave theory, where particles have definite positions at all times, guided by a real wave. It was largely ignored for decades until David Bohm revived it in the 1950s. And the many worlds interpretation, proposed by Hugh Everett in 1957, suggested that every quantum measurement causes the universe to split into branches, one for each possible outcome, all equally real. These interpretations are still debated today. Physicists who work with quantum mechanics daily, building quantum computers, designing semiconductors, developing quantum cryptography, mostly use the formalism without worrying too much about interpretation. They calculate, they predict, they build. The math works. What it means, philosophically, remains one of the deepest open questions in science. But here's what's remarkable, and what I think is worth sitting with as you settle deeper into wherever you are right now. All of this, the wave functions, the probability amplitudes, the uncertainty relations, grew out of a handful of puzzles about light and heat that people were struggling with at the turn of the 20th century. The ultraviolet catastrophe, the photoelectric effect, the spectral lines of hydrogen. Seemingly small, technical problems. And the solutions to those problems didn't just fix the immediate issues. They revealed that the universe operates according to rules that no one had imagined. Rules that violate every intuition we've built from living in the macroscopic world. And yet those rules are what make the macroscopic world possible. The stability of atoms, the structure of the periodic table, the way chemical bonds form, the reason solid matter is solid, all of it depends on quantum mechanics. The chair you might be sitting in, the bed you might be lying on, holds its shape because of the quantum mechanical behavior of electrons in atomic orbitals. And this brings us to something that connects quantum mechanics to one of the most practically important ideas in all of engineering and information theory, something that was being developed around the same time by a quiet, brilliant man working at Bell Labs in New Jersey. Because once you have a universe that runs on probability and discrete quantities, quanta of energy, binary outcomes of measurements, you're surprisingly close to the foundations of how we think about information itself. And the person who formalized that connection, who figured out how to measure information the way you'd measure energy or temperature, was Claude Shannon. And what Shannon did in 1948, in a single paper that almost nobody outside of mathematics initially understood, was arguably one of the most consequential intellectual achievements of the 20th century. He gave the world a mathematical theory of communication. And the key insight, the thing that made everything else in that paper possible, was defining what information actually is, not in the vague, everyday sense of the word, but as a precise, measurable quantity. Now, think about how strange that is for a moment. Before Shannon, people used the word information all the time, obviously, but nobody had a rigorous way to quantify it. You couldn't say this message contains exactly this much information the way you could say this object has exactly this much mass, or this circuit carries exactly this much current. Information was a fuzzy concept. Shannon made it sharp, and the way he did it is beautiful, and it connects back to everything we've been talking about. Here's the core idea. Information is about surprise, or, to put it more precisely, information is about the reduction of uncertainty. If I tell you something you already know for certain, I've given you zero information. If I tell you something you had no way of predicting, something that was genuinely uncertain before I said it, I've given you a lot of information. Shannon realized that you could measure information by asking how much uncertainty a message resolves. And the natural unit for measuring that uncertainty turned out to be the binary digit, the bit. A single yes or no question answered, 1 or 0, heads or tails, on or off. And here's where the quantum connection is more than just poetic. Remember how quantum measurements give you discrete outcomes? You measure the spin of an electron and you get up or down. You measure the polarization of a photon, and you get horizontal or vertical. These are binary outcomes. The universe, at its most fundamental level, seems to deal in discrete, probabilistic answers to yes or no questions. Shannon didn't derive his theory from quantum mechanics. He was solving a completely different problem. An engineering problem about sending telegraph signals and telephone calls through noisy wires. But the mathematical structure he arrived at has this deep resonance with the quantum world. Both are fundamentally about probability distributions over discrete outcomes. Shannon was a fascinating person, by the way. Born in 1916 in Petoskey, Michigan, a small town on the shores of Lake Michigan. Even as a kid, he was building things, a telegraph system out of barbed wire fencing that connected his house to a friend's house half a mile away. He went to the University of Michigan, got dual degrees in mathematics and electrical engineering, and then went to MIT for his master's thesis. And that master's thesis, written when he was just 21 years old, is sometimes called the most important master's thesis of the 20th century. In it, Shannon showed that Boolean algebra, the logic of true and false, and or and not, could be used to design and analyze electrical switching circuits. He basically proved that you could build any logical operation out of simple electrical switches. That thesis laid the theoretical groundwork for every digital circuit that has ever been built. Every computer, every smartphone, every digital watch. All of it traces back to a 21-year-old kid in 1937, realizing that electrical engineering and symbolic logic were the same thing. But it was his 1948 paper, A Mathematical Theory of Communication, that really changed the world. Published in the Bell System Technical Journal, it was dense, mathematically rigorous, and initially baffling to most engineers. But the ideas in it were so powerful that they gradually reshaped entire fields, not just telecommunications, but computer science, linguistics, neuroscience, statistics, even biology. So let me walk you through the key ideas, slowly, because they're worth understanding. Shannon started with a simple model of communication. You have a source that produces a message. You have a transmitter that encodes that message into a signal. The signal travels through a channel, a wire, the air, a fiber optic cable, whatever. The channel adds noise. On the other end, a receiver decodes the signal back into the message and delivers it to the destination. Source, transmitter, channel, receiver, destination. That's the whole setup. The first big question Shannon asked was, how do you measure the information content of the source? And this is where his definition of information as surprise really comes in. He introduced a quantity he called entropy. And yes, he deliberately borrowed the word from thermodynamics, partly because the mathematical formula looked identical to what Boltzmann had written down for thermodynamic entropy, and partly, as the story goes, because John von Neumann told him to use the name since nobody really understands entropy. So, in a debate, you'll always have the advantage. Shannon's entropy measures the average amount of surprise per symbol produced by an information source. If you have a source that can produce, say, 8 equally likely symbols, the entropy is 3 bits, because you need 3 yes or no questions to identify which of the 8 symbols was sent. 2 to the power of 3 is 8, so 3 binary choices pin down 1 symbol out of 8. Makes sense, right? But here's where it gets interesting. If the symbols aren't equally likely, if some are much more common than others, the entropy goes down, because you're less surprised on average by each symbol. You can usually predict what's coming. Think about English text. The letter E shows up about 12% of the time. The letter Z shows up less than 1%. So when you see an E, you're not very surprised. When you see a Z, you are. The entropy of English, per letter, is lower than it would be if all 26 letters were equally likely. Shannon actually calculated this. He estimated that English text carries about 1 to 1.5 bits of information per letter, far less than the roughly 4.5 bits you'd get if all 26 letters were equally probable. The difference is redundancy. English is highly redundant. You can drop letters, misspell words, and people still understand you. That redundancy is why autocomplete on your phone works at all. The next letter, the next word, is partially predictable from what came before. And this leads directly to Shannon's first major theorem, which is about compression. He proved that you can compress a message down to its entropy. That's the theoretical limit. But no further. You can squeeze out all the redundancy, encode the message using fewer bits, but you can never use fewer bits per symbol than the entropy without losing information. This is called the source coding theorem, and it's the reason your music files can be compressed, your photos can be made smaller, your videos can be streamed, Every compression algorithm, zip files, MP3s, JPEGs, the codecs that make streaming video possible, is essentially trying to approach Shannon's entropy limit, trying to strip away the predictable parts and keep only the surprising parts, the actual information. But here's the thing that's even more remarkable, the result that really stunned people. Shannon's second major theorem, the noisy channel theorem. He proved that for any communication channel, no matter how noisy, there exists a maximum rate at which information can be transmitted reliably. He called this the channel capacity. And the stunning part, the part that nobody expected, was that he proved you can transmit at any rate below the channel capacity with an arbitrarily small probability of error. Not zero noise, not a perfect channel. A noisy, messy, real-world channel full of static and interference and random disturbances. And Shannon proved that you can still send information through it essentially perfectly, as long as you don't try to send too fast, and as long as you use sufficiently clever encoding. Now, he didn't tell you how to build those clever codes. His proof was an existence proof. He showed that such codes must exist using probabilistic arguments. But he didn't construct them, and that drove engineers a little crazy for decades. They knew the limit was there. They knew perfect communication through noisy channels was theoretically possible. But actually, building codes that approached Shannon's limit turned out to be extraordinarily difficult. It took nearly 50 years. It wasn't until the mid-1990s that a class of codes called turbo codes, discovered somewhat accidentally by Claude and his colleagues in France, came within a whisper of the Shannon limit. And then in the early 2000s, another class called low-density parity check codes, which had actually been invented by Robert Gallagher in his 1960 PhD thesis, but forgotten because computers of that era couldn't handle them, were rediscovered and shown to also approach the limit. Today, these codes are in everything. Your cell phone uses them. Wi-Fi uses them. Satellite communication. Deep space probes talking to Earth from billions of miles away. They all rely on error-correcting codes that approach Shannon's theoretical bound. And think about what that means practically. When the Voyager spacecraft, launched in 1977, sends data back from beyond the edge of the solar system, the signal that reaches Earth is unimaginably faint. The power received by the antenna is something like 10 to the minus 16 watts, a fraction of a billionth of a watt. That signal is buried in noise, and yet we can extract the information from it perfectly because of error-correcting codes built on the foundation Shannon laid down. That's not magic. That's mathematics, applied with extraordinary care. There's something else Shannon introduced in that 1948 paper that's worth mentioning, because it ties back to the idea of entropy in a really deep way. He showed that the entropy of an information source has the exact same mathematical form as the thermodynamic entropy that Boltzmann defined. The formula involves a sum over possible states of the probability of each state times the logarithm of that probability, with a negative sign out front. In thermodynamics, this measures the disorder of a physical system. How many microscopic arrangements are consistent with the macroscopic state you observe? In information theory, it measures how unpredictable a message source is, how much you stand to learn from each new symbol. Same formula, different domain. And people have argued for decades about whether this is a coincidence, a mathematical analogy, or something deeper. There are compelling arguments that it's genuinely deep, that information and physical entropy are fundamentally related, that erasing information requires dissipating energy, that computation has thermodynamic costs. This idea was explored by Rolf Landauer at IBM in the 1960s, who showed that erasing a single bit of information must release a minimum amount of heat, a tiny, tiny amount, but non-zero. Landauer's principle, it's called. And it was experimentally confirmed in 2012. The connection between information and physics is real. So, here you are, lying in the dark, and the story has carried us from ancient Greek ideas about what things are made of, through the laws of thermodynamics and the nature of energy, through waves and light and the quantum revolution, and now to information, to the realization that the universe doesn't just contain energy and matter, it contains information, and that information obeys its own laws, laws that are mathematically intertwined with the laws of physics. And this brings us to something that Shannon's work made possible, but that required one more enormous conceptual leap, the leap from information theory to computation. Because knowing how to measure and transmit information is one thing. Knowing how to process it, how to transform it, how to use it to solve problems, that's something else. And the person who laid the theoretical foundation for that, who imagined the universal computing machine before any such machine existed, was working on the problem even before Shannon published his paper. His name was Alan Turing, and the story of what he figured out, sitting in a garden in Cambridge in 1936, reading a paper about the foundations of mathematics, is one of those moments where a single person's thought reshapes everything that comes after. Turing was 23 years old, a graduate student at King's College, Cambridge, and the problem he was wrestling with wasn't about building machines at all. It was about mathematics. Specifically, it was about a question that the great German mathematician David Hilbert had posed years earlier, a question called the Entscheidungsproblem, which is German for the decision problem. And the decision problem asked something that sounds almost innocent. Is there a mechanical procedure, a step-by-step method that can determine whether any given mathematical statement is true or false? Hilbert believed the answer was yes. He believed that mathematics was, at its core, a complete and consistent system, and that you could, in principle, build a kind of logical machine, not a physical machine, just a procedure, that could grind through any well-formed mathematical proposition and eventually spit out true or false. It was a beautiful dream, and Turing destroyed it. But here's the thing. The way he destroyed it was more important than the destruction itself. Because in order to prove that no such universal decision procedure could exist, Turing had to define, with absolute mathematical precision, what a mechanical procedure even meant. What does it mean to compute something? What does it mean to follow a step-by-step process? These seem like obvious questions, the kind of thing you'd think mathematicians had already nailed down. But they hadn't. Not rigorously. And Turing's answer to that question, his definition of computation, turned out to be one of the most consequential ideas of the 20th century. What he imagined was breathtakingly simple. Picture an infinitely long strip of tape divided into squares. Each square can hold a symbol, let's say a 0 or a 1, though you could use any finite set of symbols. There's a read-write head that sits over one square at a time. The head can read the symbol on the current square, write a new symbol, and then move one square to the left or one square to the right. That's it. The head's behavior is governed by a table of rules. If you're in state A and you read a 1, write a 0, move right, and switch to state B. If you're in state B and you read a 0, write a 1, move left, and switch to state A, and so on. A finite number of states, a finite number of rules, an infinite tape. This is a Turing machine. And you might think, okay, that's a cute little thought experiment, but what can something that simple actually do? And the answer that changed the world, is everything. Every computation that any computer has ever performed or ever will perform can be carried out by a Turing machine. Your smartphone, the most powerful supercomputer on Earth, the laptop you use for email, they are all in terms of what they can compute, equivalent to Turing's imaginary tape machine from 1936. They're faster, obviously, enormously faster. They have more memory. They have screens and keyboards and wireless connections. But in terms of the fundamental question of what is computable, what problems can be solved by following a mechanical procedure, they can't do anything that Turing's simple machine can't do. This is the Church-Turing thesis, named for Turing and the American mathematician Alonzo Church, who arrived at an equivalent result around the same time using a completely different approach called lambda calculus. And the fact that two people working independently, using totally different formalisms, arrived at the same boundary of computability, that's a strong hint that they found something real, something fundamental about the nature of computation itself. But Turing went further. He didn't just define a Turing machine. He defined a universal Turing machine, and this is where it gets really beautiful. See, each specific Turing machine has its own fixed table of rules. One machine might add 2 numbers, another might check whether a number is prime, another might sort a list. They're all different machines with different rule tables. But Turing showed that you could build a single machine, one machine, that could simulate any other Turing machine. You just feed it a description of the machine you want to simulate, encoded as symbols on the tape, along with the input data, and the universal machine reads that description and faithfully carries out whatever the described machine would do. Think about what that means. It means you don't need a different machine for every task. You need one machine that can be reprogrammed, one machine that reads instructions, a program, and executes them. That's a computer. That's the idea. Turing invented the concept of software, not the word, not the implementation, but the concept, the realization that a single general-purpose machine could perform any computation, depending on what instructions you gave it. And here's the kicker. He did this to prove a negative result. He was trying to show that certain problems are undecidable, that no algorithm can solve them. And the specific problem he proved undecidable is called the halting problem. Given a description of a Turing machine and an input, will that machine eventually halt, stop running, or will it run forever? Turing proved, using a gorgeous diagonal argument reminiscent of Cantor's proof that some infinities are bigger than others, that no general algorithm can answer this question for all possible machines and inputs. There will always be programs whose behavior you cannot predict without actually running them. Computation has limits, and those limits are not engineering limits, not about speed or memory or cleverness. They're mathematical limits, as fundamental and unbreakable as the laws of thermodynamics. Now, Turing published this in 1936, and it was a purely theoretical paper. No one built a Turing machine. It was a mathematical construct. But 3 years later, the world went to war, and Turing's abstract ideas about computation suddenly became desperately, urgently practical. Because the Germans were using a machine called Enigma to encrypt their military communications, and the British needed to break that encryption. Turing went to Bletchley Park, a country estate north of London that had been requisitioned as the headquarters of Britain's code-breaking operation, and there he became one of the central figures in one of the most important intelligence operations in history. The Enigma machine was an electromechanical device. It used rotating wheels, or rotors, to scramble messages. Each time you pressed a key, the rotors would advance, changing the substitution pattern. The number of possible settings was astronomical, on the order of 150 million, depending on the version. Brute force was out of the question. But Turing and his colleagues, building on earlier work by Polish cryptanalysts Marian Rejewski, Jerzy Różycki, and Henryk Zygalski, whose contributions are sometimes underappreciated, developed methods to dramatically narrow down the possibilities. Turing designed a machine called the bomb, an electromechanical device that could test potential Enigma settings at high speed, looking for logical contradictions that would rule out incorrect configurations. It wasn't a computer in the modern sense. It was a special-purpose machine. But it worked. By the middle of the war, Bletchley Park was routinely reading German military communications, and historians estimate that this intelligence, codenamed Ultra, shortened the war by at least 2 years and saved millions of lives. After the war, Turing turned to building actual computers. He wrote a detailed design for the Automatic Computing Engine, or ACE, at the National Physical Laboratory in London. His design was remarkably forward-looking. It emphasized speed and a large instruction set, and it included ideas about subroutines and programming that were ahead of their time. But Turing was difficult to work with, impatient with bureaucracy, and the project moved slowly. Meanwhile, at the University of Manchester, a team led by Frederick Williams and Tom Kilburn built one of the world's first stored program computers, the Manchester Baby, which ran its first program on June 21, 1948. Turing eventually moved to Manchester and worked on programming and on the theoretical question that fascinated him most in his later years. Could machines think? His 1950 paper, Computing Machinery and Intelligence, is one of the most famous papers in the history of science. In it, he proposed what he called the imitation game, now known as the Turing test, as a way to evaluate machine intelligence. Instead of asking the philosophically loaded question, "Can machines think?" he suggested a practical test. If a human judge, communicating by text with both a human and a machine, cannot reliably tell which is which, then the machine should be considered intelligent. It was a characteristically elegant sidestep of a messy philosophical debate, and it's still discussed, debated, and argued about today, especially now that large language models can carry on conversations that are, at times, remarkably human-sounding. But Turing's story has a tragic dimension that you should know about. In 1952, he was prosecuted for homosexuality, which was then a criminal offense in Britain. He was convicted and given a choice between prison and chemical castration through hormone injections. He chose the injections. 2 years later, on June 7, 1954, he was found dead in his home, a half-eaten apple beside his bed. The cause of death was cyanide poisoning, and the inquest ruled it a suicide, though some people close to him believed it may have been an accident. He was known to be careless with chemicals in his home laboratory. He was 41 years old, one of the greatest minds of the 20th century, a man who had helped save millions of lives and who had laid the theoretical foundations for the entire digital age, was hounded to death by his own government for who he loved. In 2009, the British Prime Minister issued a formal apology, and in 2013, Turing received a royal pardon. But of course, none of that changes what happened. So let's step back now. Let's take a breath. Because over the course of this long, winding conversation, we've traveled an enormous distance together. We started with something as basic as the question, what is energy? A question the ancient Greeks asked, a question that took centuries to answer properly. We watched the idea of energy crystallize through the work of Joule and Carnot and Clausius and Boltzmann, and we saw how the laws of thermodynamics, those unbreakable rules about energy and entropy, govern everything from steam engines to the heat death of the universe. We followed energy into the world of waves, where Fourier showed us that any complex signal can be decomposed into simple sine waves, and where the interplay of frequency and resonance governs everything from musical instruments to the power grid. We watched light reveal itself as a wave through Young's double slit and Fresnel's mathematics, and then we watched it refuse to behave as a wave when Planck and Einstein showed that energy comes in discrete packets, quanta, and that light is somehow both wave and particle, depending on how you look at it. We followed that mystery into the heart of quantum mechanics, where Heisenberg and Schrödinger built two different mathematical frameworks that turned out to be the same framework in disguise, where Born told us that the wave function gives us probabilities and nothing more, and where the uncertainty principle, which is really just Fourier analysis applied to matter waves, sets fundamental limits on what can be known. And then we crossed into information theory, where Shannon showed that information itself can be measured, quantified, compressed, and transmitted with perfect reliability through noisy channels, and where the formula for information entropy turned out to be mathematically identical to the formula for thermodynamic entropy. A coincidence that isn't a coincidence at all, as Landauer showed when he proved that erasing information has a real, physical, thermodynamic cost. And finally, we arrived at computation, where Turing showed that a ridiculously simple imaginary machine, a tape, a head, a table of rules, can compute anything that is computable, and that some things are not computable at all, no matter how powerful your machine. And here's what I want you to notice. Lying there in the dark, maybe half asleep, maybe still following every word. All of these ideas are connected. They're not separate subjects taught in separate classrooms by separate professors. They're one story. Energy is conserved but degrades into entropy. Entropy measures disorder, but also measures information. Information can be processed by computation, but computation has fundamental limits. Waves carry energy and encode information and exhibit quantum behavior. The uncertainty principle connects wave mechanics to information theory through Fourier analysis. Planck's constant bridges the wave and particle descriptions of reality. Shannon's theorems set the rules for communication. Turing's work sets the rules for computation. Landauer's principle ties information back to thermodynamics. It's all one fabric. And the beautiful thing, the really beautiful thing, is that none of these ideas are beyond you. They never were. They were just never explained to you slowly enough, patiently enough, with enough context and enough story. The math can be challenging, sure, but the ideas are human-sized. They were figured out by human beings, flawed, brilliant, stubborn, sometimes tragic human beings, who asked simple questions and refused to accept hand-wavy answers. What is energy? What is light? What is information? What can be computed? These are questions a child might ask, and the answers turned out to be among the deepest truths we've ever found. So if you're still awake, I hope some of this has settled into you in a way that feels right. Not memorized, but understood. The way you understand that heavy things are hard to push or that hot coffee cools down if you leave it alone. And if you drifted off somewhere along the way, during the bit about entropy maybe, or somewhere in the middle of Fourier's heat equation, that's perfectly fine. That's what this was for. The ideas will be here whenever you want to come back to them. They've been here for a long time, woven into the fabric of the universe, waiting patiently for someone to notice them. And now you know, at least a little,